According to the Fundamental Theorem of Calculus, integration and differentiation can be thought of as inverse operations. Differentiating an integral and integrating a derivative yield almost identical results. For example, the derivative of the integral of 3x squared dx is equal to 3x squared. And the integral of the derivative of 2x to the fourth plus 7 dx is equal to 2x to the fourth plus c. Function types such as polynomial functions, exponential functions, and trigonometric functions have their own differentiation and integration formulas. When it comes to techniques, however, integration and differentiation can be quite different. In general, when taking a derivative, if the function is a polynomial, use the power rule. If it is a product, use the product rule. If it is a quotient, use the quotient rule. And if it is a composite, use the chain rule. It doesn't work that way with integration. There's no rule specifically for integrating a product or a quotient. Part of the reason is that the product, quotient, and chain rules all incorporate parts of the function being differentiated, as well as the derivatives of those parts. So when looking at an integral, it's difficult to tell which rule needs to be undone. Fortunately, there is a useful technique that involves substitution. Let's begin with an example. At first glance, this seems like a quick polynomial integration, right? Look closely. In order to integrate this as a polynomial, we would need to expand 4x squared minus 13x to the fifth power, then distribute the 8x minus 13 to that gigantic result. A huge amount of work. Notice that 8x minus 13 is the derivative of 4x squared minus 13x. This tells us we can use substitution. Traditionally, the variable u is used in this technique, so it is often called u substitution. So here's the big idea. First, we're going to assign a part of the function to be u. Then we'll rewrite the integral in terms of u, not x, creating an easily integrable form. Then we'll integrate, and finally we'll convert the result back to being in terms of x. First, identify the part of the function that is the derivative or multiple of the derivative of the other. Once this is identified, the other piece will be u. Typically, this involves thinking a little bit ahead and making a choice. In this case, since 8x minus 13 is the derivative of 4x squared minus 13x, we'll call 4x squared minus 13x our u. So u is equal to 4x squared minus 13x. Then we'll take the derivative of this and get that du is equal to 8x minus 13 dx. This gives us everything we need to rewrite the integral in terms of u. So we're going to have our u is right here, this part, not including to the fifth power. And then our du is this part and this part. So if we rewrite this integral, we get the integral of u to the fifth power. Remember, we didn't include that, du. Now this becomes something that can be easily integrated. So this is equal to 1/6 u to the sixth plus c. All that's left is to rewrite the result in terms of x, which involves substituting 4x squared minus 13x for u. So we have this is equal to 1/6 times 4x squared minus 13x to the sixth power plus c. Remember, you can always take the derivative to check your result. Let's try another. At first glance, there are many possibilities for u. X minus 4, x minus 4 cubed, x squared minus 8x, x squared minus 8x to the 1/3 power, but there's only one that has the necessary relationship. Let's take a look at the derivative of x squared minus 8x. This gives us 2x minus 8, which then can factor to be 2 times x minus 4. Since x minus 4 is a multiple of the derivative of x squared minus 8x, x squared minus 8x must be our u. So u is equal to x squared minus 8x. And du is equal to 2x minus 8, which is 2 times x minus 4 dx. Notice that there's no 2 in the original integral. No problem, just divide by 2. So 1/2 du is equal to x minus 4 dx. Make the substitutions and simplify a little bit. So notice up here we have our u is x squared minus 8x, so that's this portion. And then our du, or 1/2 du, is x minus 4 dx. Now let's substitute in our u's. The integral of 6 u is equal to x squared minus 8x, which is this part, cube rooted, or we can say to the 1/3 power, it means the same thing, times our blue part right here, which we said is 1/2 du. When we simplify this, we get the integral of 3u to the 1/3 du, which is equal to u to the 4/3, 3u to the 4/3 times 3/4 plus c, which is equal to 9/4 u to the 4/3 plus c. Now we're going to rewrite this in terms of x. So we have 9/4 times u to the 4/3, remember u is x squared minus 8x, to the 4/3 plus c. Let's work one final problem together. The temptation here is to say that the answer is sine of 9x plus c, since we know the derivative of sine x is cosine x. But we need to account for the 9x in the parentheses since it is a function. Clearly, we can't make u equal to cosine of 9x because there's no negative sine function in the integral. So if our u is equal to 9x, then du must be equal to 9 dx. But there's not a 9 in our function, so we're going to take 1/9 du is equal to dx. Now let's work on rewriting our integral. So our u is 9x, which is this part right here, and our du, or our 1/9 du, is this part right here. So plugging that into our integral gives us the integral of 1/9, because remember it's 1/9 du, cosine of u du. Now we're going to integrate. So this is equal to 1/9 sine of u plus c. And finally, we're going to substitute in our u value again. So this gives us 1/9 sine of u is equal to 9x, so 9x plus c. Here's one for you to try. Using substitution, find a formula for the antiderivative of the tangent function. So the integral of tangent of x dx is equal to the integral of sine x over cosine x dx. Pause the video and try this one for yourself. Okay, so first thing we need to do is choose our u carefully because du cannot be in a denominator. So our u is going to be cosine x, which then means that our du is equal to negative sine x dx. Now there's not a negative sine x in our function, so we're going to make this negative du by dividing both sides by -1 equals sine x dx. Now let's rewrite our function. So our u part, cosine of x, is right here in our denominator. And our negative du is this part right here in our numerator, and our dx right here. So when we rewrite this, we'll have the integral of u is in our denominator, so 1 over u, times negative du, so we'll put du back here and I'm going to put the negative in front. When we integrate this, we get the negative natural log of u plus c. Finally, we're going to rewrite this in terms of x. So this is equal to negative ln of the absolute value of our u, which is cosine x, plus c. Be sure to integrate the method of substitution into your calculus repertoire. It is one of the key ways of finding antiderivatives. I hope you enjoyed this video. Thanks for watching and happy studying.